Imagine materials that can heal themselves, structures that assemble autonomously, or devices that adapt to their environment without human intervention. This isn't science fiction. It's the transformative promise of 4D printing, a revolutionary field where the fourth dimension, time, is meticulously engineered into the very fabric of objects. 4D printing extends the capabilities of traditional 3D printing by incorporating a temporal element. Unlike static 3D printed objects, 4D printed structures are designed to change their shape, properties, or function over time. This dynamic behavior is triggered by specific external stimuli, making these objects truly adaptive. This innovation moves beyond mere fabrication to the creation of active, responsive systems. It represents a paradigm shift from passive components to intelligent, reconfigurable structures. For engineers and designers, this opens up unprecedented possibilities for functional design. The heart of 4D printing lies in its smart materials. These advanced composites are engineered to exhibit predictable and repeatable changes when exposed to specific environmental cues. Understanding their mechanisms is crucial for effective design and application. Shape memory. Polymers are perhaps the most well-known smart materials in 4D printing. They possess the remarkable ability to return from a temporary, deformed shape to a pre-programmed permanent shape upon exposure to a specific stimulus, typically heat. This transition is governed by their glass transition temperature, TG. Below their TG, SMPs are rigid and can be deformed and locked into a temporary shape. When heated above their TG, the polymer chains regain mobility, allowing the material to recover its original permanent form. This process is highly repeatable and offers significant design flexibility. Hydrogels are polymer networks that can absorb and retain large amounts of water, swelling significantly in the process. Their response is primarily to moisture or changes in pH. The degree of swelling is determined by the polymer's cross-linking density and its chemical affinity for water. By strategically printing hydrogels with varying densities or compositions, designers can create complex, pre-programmed bending or folding motions when the material is immersed in water. This makes them ideal for biomedical applications and soft robotics. While SMPs are a type of thermo-responsive material, this category also includes other polymers that undergo phase transitions or significant property changes with temperature fluctuations. These materials might change stiffness, color, or even transparency. Their response is often reversible. Engineers can leverage these materials to create components that adapt to temperature variations in their operating environment. This could range from self-regulating ventilation systems to adaptive thermal insulation. Photoresponsive materials change their properties when exposed to specific wavelengths of light. This change can involve a shift in molecular structure, leading to macroscopic deformation or an alteration in chemical reactivity. Azobenzene derivatives are common examples. The precision of light as a stimulus allows for highly localized and controlled activation. This offers exciting prospects for microactuators, reconfigurable optical devices, and even light-driven soft robots. These materials respond to electric or magnetic fields. Electro-responsive polymers, such as dielectric elastomers, can deform significantly when an electric voltage is applied. Magneto-responsive materials, often composites containing ferromagnetic particles, can change shape or stiffness in the presence of a magnetic field. The ability to control these materials remotely and instantaneously with fields makes them highly attractive for applications requiring precise, non-contact actuation. This includes advanced robotics, haptic feedback systems, and adaptive structures. 4D printing leverages established 3D printing technologies, but with critical considerations for smart material handling and precise deposition. The choice of printing method significantly impacts the achievable resolution, material properties, and complexity of the final dynamic structure. Fused filament fabrication, FFF, or fused deposition modeling, FDM, is a widely accessible 3D printing method. It involves extruding a thermoplastic filament through a heated nozzle, layer by layer. For 4D printing, specialized filaments incorporating smart materials are used. The challenge lies in ensuring the smart material properties are not degraded by the heating process and that the material flows consistently. Print parameters like temperature, speed, and infill patterns become critical design variables, influencing the final shape-shifting behavior. Stereolithography, SLA, digital light processing, DLP, and LCD-based printing utilize a liquid photopolymer resin that cures and solidifies when exposed to specific wavelengths of light. This method offers high resolution and intricate detail, making it suitable for complex 4D designs. For 4D printing, the resin itself is formulated with photocurable smart materials or composites. The precise control over light exposure allows for the creation of spatially varying material properties within a single print, enabling highly sophisticated and localized responses. The true magic of 4D printing lies in the pre-programmed stimuli response. This isn't random change, it's a meticulously designed transformation. The object's final dynamic behavior is encoded during the design and printing phases, making it a testament to advanced material science and computational design. Engineers and researchers employ sophisticated computational tools to design 4D printed objects. Finite element analysis, FFEA, and other simulation techniques are used to predict how a material will deform under specific stimuli, considering factors like material anisotropy, print orientation, and geometric constraints. This iterative design process allows for optimization of the structure's geometry and material composition to achieve the desired shape change. It's about understanding the interplay between material properties, structural mechanics, and external triggers. The programming of a 4D print involves several key elements. Material selection, choosing the appropriate smart material for the desired stimulus and response. Geometric design, designing the object's shape, hinges, and internal structures to facilitate specific bending, folding, or expansion. Print orientation, the direction in which layers are deposited can introduce internal stresses that, when released by a stimulus, drive the shape change. Multi-material printing, combining different smart materials or smart and passive materials within a single print to create complex, multi-stage transformations. By carefully controlling these parameters, designers can dictate not only if an object changes shape, but how and when it does so. The potential of 4D printing spans numerous sectors, promising revolutionary advancements for engineers, designers, students, and researchers alike. Its ability to create adaptive, responsive systems is a game changer. In healthcare, 4D printing offers unprecedented opportunities. Imagine adaptive implants that conform to a patient's changing anatomy, or drug delivery systems that release medication precisely when triggered by internal body conditions. Self-expanding airway splints could revolutionize respiratory care, while tissue scaffolds could actively guide regeneration. Researchers are exploring self-folding surgical tools and micro-robots for minimally invasive procedures. The biocompatibility and responsiveness of hydrogels make them particularly promising for these applications, enabling personalized and dynamic medical solutions. The aerospace industry demands materials that are lightweight, strong, and adaptable. 4D printing could lead to responsive carbon fiber engine inlets that optimize airflow based on flight conditions, or wing components that actively change shape to improve aerodynamic efficiency. Flexible metal fabrics for spacesuits could offer enhanced mobility and protection. This technology could also enable deployable structures for satellites or reconfigurable antenna arrays, reducing launch volume and increasing operational flexibility. The ability to adapt to extreme environmental conditions is a significant advantage. For designers, 4D printing opens up a new realm of interactive fashion. Clothing could adapt to the wearer's body shape, regulate perspiration based on temperature, or even change color in response to environmental cues. This moves beyond static garments to truly dynamic wearables. Imagine shoes that adjust their cushioning based on activity, or sportswear that optimizes ventilation as body temperature rises. This fusion of aesthetics and functionality promises a new generation of smart apparel. In the automotive sector, 4D printing could lead to intelligent components that enhance safety and performance. Consider intelligent airbags that can anticipate impact direction and deploy optimally, or self-healing body panels that repair minor damage. Adaptive interior components could adjust to passenger preferences, while responsive aerodynamic elements could improve fuel efficiency. The potential for creating more resilient and intelligent vehicles is immense. The vision of self-assembling structures is a compelling one for civil engineers. 4D printed components could be designed to unfold or interlock autonomously on-site, reducing construction time and labor costs. This could be particularly useful for rapid deployment in disaster zones or for complex architectural designs. Furthermore, smart infrastructure could monitor its own structural integrity and self-repair minor cracks, extending the lifespan of buildings and bridges. This represents a shift towards more resilient and sustainable construction practices. Soft robotics is a field that heavily relies on flexible, compliant materials to create robots capable of complex, adaptive movements. 4D printing is a natural fit, enabling the fabrication of soft actuators and grippers that can deform and interact with delicate objects without causing damage. These robots could navigate complex environments, perform intricate tasks in confined spaces, or even mimic biological movements. The ability to pre-program complex deformations makes 4D printing a cornerstone for the next generation of bio-inspired robots. While the potential of 4D printing is vast, it is still an emerging field facing several challenges. Material development remains a key area, focusing on creating new smart materials with enhanced responsiveness, durability, and scalability. The cost of specialized smart materials can also be a barrier. Furthermore, the complexity of designing and simulating multi-stimuli responsive systems requires advanced computational tools and a deeper understanding of material structure interactions. Standardization of design principles and manufacturing processes will be crucial for widespread adoption. Despite these hurdles, the rapid pace of research and development suggests a future where 4D printed objects are commonplace. As material science, additive manufacturing, and computational design continue to converge, 4D printing will undoubtedly unlock new frontiers in engineering, design, and scientific discovery. 4D printing is not just an evolution of manufacturing, it's a revolution in how we conceive and create functional objects. For engineers, designers, students, and researchers, this field offers an unparalleled opportunity to shape the future of adaptive technologies. The ability to imbue materials with intelligence and dynamic behavior promises solutions to some of the world's most pressing challenges, from personalized medicine to resilient infrastructure. Dive deeper into this transformative technology. Explore academic papers on smart materials, experiment with open-source 4D printing simulations, or consider specializing in advanced manufacturing. Share your insights and questions in the comments below, and join the global community pushing the boundaries of what's possible with adaptive materials. Your contributions are vital to realizing the full potential of 4D printing. Hey, if you're enjoying this video and want to see more like it, don't forget to hit subscribe and turn on the notification bell so you never miss an update.